All right, so we're going to go back to Microsoft Excel, and we want to go to our folder here. It's Millikan's oil drop. And yes, in your folder, you should have Millikan oil drop second analysis. If you don't have it, I need to email it to you, okay? But you don't have to have this one. Normally what we would do is we would take the data and we would just put the data inside of these holding blocks here, okay? So I would ask for 2 fall velocities and 2 rise velocities, and then these graphs will be plotted. But look, Graphical is plotting it for us immediately. So let's just put in our average velocities. We just found we found 2 rise velocities. All we have to do is just pull this open. We have if you see here, we have 1.606 for the first rise velocity. So let me just double tap, 1.606. And remember, that's E. E is for scientific notation. Computers understand that, and that's to the 4th. Then the next one, I believe, is, look at this, it's 1.579, E -4. So let's put that in. And it's rising, that's why you can tell that it's positive. So this is going to be 1.579. I believe that's how it goes. E, and then we have a -4. All right, we only have 1 fall velocity, okay? So that fall velocity is here. It's a -4.040 E -5. So we're going to put that in. And your data should be different. -4.040 E -5. And if we had another one, it would work out fine. I'm just going to make sure that my average is only concerned with B2. Okay, so that'll be fine. Yours will be different, so I'll share that with you guys. Better yet, I'll put it right below this video. So that's where this Excel spreadsheet will be. The older one doesn't have Avogadro's number in it. It just has charge. So all the way throughout, you're going to see that I put all the formulas in for you guys, and we ultimately want to calculate the radius, and then the mass, okay, and then the charge is here. And so we calculated the charge, and the charge is coming out to be 6.84 E -19. All right, the accepted value for charge is 1.60 E -19. So the number of charges that were on that particular oil droplet were 4. And this is valid. This is valid up to 5 charges, okay? This is good. And Avogadro's number. So this is, and what's the importance behind Millikan's oil drop experiment? Not to make it long, but he quantified electric charge. We found that charge comes in discrete values of 1.60 E -19 coulombs. Now, we can use this value to calculate Avogadro's number. And you guys may or may not know what Avogadro's number is, but I'm going to go ahead and see if I can help explain it a little bit. But Avogadro's number is the number of molecules per gram. And you know what? I really need to go and look at this. Let me pull it up. I have it. Oh, nope, that's not what I want. It's right here. Okay. How you doing there, Courtney? So let me just read this real quick about Avogadro's number. And it says the measurement of charge of an electron also permits the calculation of Avogadro's numbers. This is what I'm trying to do right here. It says the amount of current required to electrodeposit 1 gram of equivalent of an element on an electrode. This is called the Faraday. It's equal to the charge of an electron multiplied by the number of molecules in a mole. Okay. So through electrolysis experiments, the Faraday has been found to be 2.895 times 10 to the 14 electrostatic units, ESU units per gram of equivalent weight. We're not using that one. We're going to stick with the MKS system. So The more commonly expressed one for the MKS system is here. It's 9.625 times 10 to the 7th coulombs per kilogram. So we're more familiar with that. And if we divide this Faraday, which is what this is, coulombs per kilogram, if we divide this by the charge of an electron, we can find Avogadro's number. So this yields 6.025 times 10 to the negative 23 molecules per gram of equivalent weight, or Avogadro's number. So this is the number of moles that would be in that particular element. So we used our charge, okay, the unit of charge, which is here, and we came up with a measured value for Avogadro's number. And this is the accepted value, and I actually had 2.3, and I believe the accepted value, I thought it was 2.2 all this time, but I'm going to go ahead and put 2.5 since this is what I see. And so now, and let me change the number of decimal places being shown here. Let's give ourselves at least 3. So based on what we have here, we have our unit of charge, okay? And this unit of charge is coming from the other page here. It's based on what we actually calculated as far as the charge, and then we just divided it by the number of charges. But we are going to keep, we essentially rounded this number of charges to the greatest or the lowest. So it's approximately 4 charges on there. So if we go back to Avogadro's number, you'll see that we have our unit of charge, we have our measured Avogadro's number, and that's molecules per gram, and this is that's our measure, and then we have our accepted value. So the percent difference between those two is 0.16%. This is awesome. So you guys just turn this in, and that'll be super sufficient.